with calorimetry, although we will use it short or quite a bit. Now we're going to look on what happens when we don't have the ability to do calorimetry or where we want to do predictions. And that is what we're going to spend the next week or so on. Okay, so calorimetry is the stuff that we can do reasonable. I'm not able to do uh, combustion reactions in my lab because of a lack of equipment. So I have to use uh, a modified form of doing this. I can't burn magnesium in one of my calorimeters, it just doesn't work. So we're going to use that and something we can do in our calorimeters and this idea of Hess's law. Okay. So explain and use Hess's law to calculate energy changes for a net reaction. That's our learner outcome. Okay, we talked about this. The other thing is we can't study the rusting of iron, the oxidation of iron, because it takes over a long time. Uh, so we have two methods that we're going to use. Both of them rely on an existing principle. And that is basically that it doesn't matter what pathway something uses to get to the final point, only the difference between where it started and where it ends. You can think of this like me traveling to Edmonton. I can go through Grand Prairie and then the double lane all the way through, or I could go through Peace River, High Prairie, Slave Lake, down to Edmonton. But the total distance that I am from my starting point is still the same, whatever it is, 480 kilometers or something like that. It was independent. The distance that I am from where I started, my displacement, to use physics words, is the same whatever pathway I take. And the same thing talks about energy here. We can have a basic reaction, for example, the one we write for photosynthesis. We have we have a product and a reactant. Now, I think biology, the different stages of photosynthesis is in Bio 20, but I'm not sure on that. But it's about 19 different stages that have to happen for you to get from carbon dioxide and water to glucose. So, but the overall energy change, whether we are able to go from the reactants to the products right away, or if we have to go through 19 stages, we still end up with the same amount of energy given off absorbed in that case. Okay, so that's the principle that we're going to be using. A change in the system or the net property of some system are independent of the way that the system changes from the initial to the final, going directly or going from going directly or going in a different pathway. Now, we call this Hess's law because he was the first to summarize this in terms of energy. The addition of chemical reaction yields a net chemical change, chemical equation whose enthalpy change is the sum of the individual positive and negative. We'll show you what exactly that means. But basically, you have this reaction, you have this reaction, you have this reaction, you have this reaction. And they're happening in certain steps. If you want to go from the reactants here to the products here, how much energy is given off or absorbed? Well, we add up all the different energies of those chemical reactions that we're going to use. So one of the example that I'm using in a second, we cannot study how much energy is given off when carbon reacts with oxygen to give you carbon monoxide, because it never just gives you carbon monoxide. But you can combust carbon monoxide with oxygen to get an energy change that you can measure. You can burn carbon with oxygen to get carbon dioxide, but you can't get that first step. So how do we study that? That's what we're talking. That's what the use is right now. So, as I said, here's our potential energy diagram without a title, so I lose marks. We can study this reaction. We know that that energy is going to be 393.5. We're able to study this reaction, carbon monoxide plus oxygen to give you carbon dioxide. We know that one is 283. Yeah. We were able to study this one because it can happen. Oops. So 283. What we can find by thinking about this plus this gives you the entire thing. We're able to figure out what this energy is, 110.5. Okay, so this is that idea of Hess's law. It doesn't matter if I study if it goes from here to here, then to here, or if it goes from there to there right away. It's the overall energy change is still going to be 393.5 kilojoules for every mole of carbon dioxide created. Now, here's the mathematical bunch of big, ugly looking things, but it is essentially what we're doing here. The total energy change, delta T H, is equal to the energy change for the first reaction, plus the energy change for the second, plus the energy change for the third, plus the energy change for the fourth. Now, here's a notation, a mathematical notation that we may not have seen. This funky looking E, it is the sigma notation. I guess you would have seen it a bit in math last year. It means the sum of all of these reactions. So the sum of this stuff. And we have delta RH, we have an equation for delta RH and delta RHM. The sum of all the N delta RH, all of the all of the number of moles times the molar enthalpy. That's the idea of Hess's law. Now we're going to use this, getting used to these headphones for right now. They're making me sweat. We're going to use this on our next step. So the overall energy change will be the same if it occurs in one step or multiple steps. All it says. Now, method number one for Hess's law is when you have access to chemical reactions, certain chemical reactions. Okay? So, think about what we do to a chemical reaction. If I balance it with twice as much energy, twice as many moles as Jamie does, what happens to my energy? How much energy do I get out in comparison to the way that Jamie balanced the equation? Twice as much. So if I multiply a chemical reaction by a constant, I must multiply the energy given off by that constant. We would never use molar enthalpy change here. We're just going to use delta RH, or we're going to put the energy in the chemical, or as a thermochemical equation. Now, if I change the direction, the big example that we use a lot is photosynthesis and cellular respiration. What happens to the energy change if you take photosynthesis, which is an endothermic reaction, and you run the reaction the other way? What happens to the energy type? Well, photosynthesis is endothermic, and what do we use that plant-based sugar for? We use it for energy in combustion, or in cellular respiration. So it's endothermic when it's photosynthesis, and exothermic when it's cellular respiration. You change the sign. That's how we indicate that, but it just changes the type of reactions occurring. If you flip the reaction, the type of reaction changes. Okay, so here we have, all right, and blah, blah, blah. Here's the stuff that we want. Now, we already know this because we chatted on the other side. We knew it's 110, okay? or you can get it's 110 from that. We want to know how much energy is given off when this reaction occurs. Now this again, because it is never going to occur by itself, it always occurs in the presence of carbon, this reaction at the same time, this reaction at the same time, we can't study it. We're going to take these two reactions and we're going to flip them, add them together to get that reaction, which will allow us to get that that energy. So what we want to do here, I need carbon monoxide. So to me, carbon monoxide is my most important. It's the interesting one. I need it on my right-hand side. Well, carbon monoxide only occurs in this chemical reaction. So I'm going to have to flip this reaction. I'm going to have to take reaction. I said that. Is this not on? I'm going to have to flip it and multiply it by 1/2 because I only want one carbon monoxide on that side. Now we'll talk about how to get the rest of it, but that's the significant one for me right now. So I have two, no, I don't. I have one CO2 giving me one carbon monoxide. And 1/2 oxygen. Now, the other thing is, now I try to look, I need carbon on that side. Okay. Now, there's two couple ways of looking at it. I need carbon on that side, or I need to get rid of this CO2. We'll talk about, since I need carbon on that side, and this is the only place the carbon comes in, I can just write down equation number 1. Carbon plus oxygen yields CO2. Now, we'll show you what I mean in a second, but let's talk about our energy here. I just wrote down the reaction for number 1, so the energy change is still negative 393.5. I flip this reaction, so the energy is now an exothermic reaction, and I multiplied every entity in that reaction by 1/2. So I also multiply the energy. That ain't right. All right. So I multiplied the 566 by 1/2, and I changed the sign to indicate that this is an endothermic process. Now, before we add up those ones, if we add these two reactions together, now I'm going to list this. I'm going to list everything I have, and then I'm going to cross stuff off. I don't often do this, but I will now to start with. I have one carbon. I have one oxygen and one carbon dioxide. On this side, I have one carbon monoxide plus 1/2 an oxygen plus carbon dioxide. Okay. Now, the reason why we're going to cancel things off, a chemical equation, we want to indicate the things that change. Okay, so if you've got carbon dioxide on this side and carbon dioxide on this side, they don't change. So why write them down? You can think of them as canceling. They're going to cancel each other off. They haven't changed. So why bother writing them down? Here I have a full oxygen, and over here I have a half an oxygen. So this guy, half of this oxygen did not change. Which, now we have what we want. 1 carbon plus 1/2 oxygen yields carbon dioxide gas, sorry, carbon monoxide gas. So by not writing the things that don't change in this system, we've got it. And then when we add these together, because we're going to add the energy, that's what we're looking for. We're going to add the energies, and we end up with our negative 110.5 kilojoules. Now, I can't remember if I asked for kilojoules per mole or not. Molar, okay. So because we're asking for the molar enthalpy, we're not quite done the question. We're more or less done the question, but not quite. The molar enthalpy is equal to the 110.5 kilojoules divided by the 1 mole of carbon monoxide that we created. So we have 110.5 kilojoules per mole. Sorry for shoving it in the corner. This is a bit of an art. Yeah, I've done this one so many times, I know exactly what I'm doing. But you have to look at it and say, okay, what's important in our reactions here? I looked at the CO2. I could figure out how to get the CO2 in the proper spot and in the proper number, proper amount. And in this case, I also had carbon, same thing. Sometimes I'll have to cross stuff off. Sometimes I'll have to change the state, most often water. Okay, maybe if I give you the reaction to give you gaseous water, but I want the final answer in liquid water, I've got to take that energy into account. Okay, so write the equation. Okay, so summary, what do? Write the net equation. What do you want to find the energy for? Or what do I want you to find the energy for? I can ask you to write 3 types of equations. Combustion, formation, and simple decomposition. I can describe the reaction for you, so that would be a 4th way of doing it. You are going to manipulate the reaction so they add up to, so they get you the net reaction. If I need dinitrogen tetraoxide over here, I may have to flip an equation and divide it by 2, multiply by half, divide by 2, but I like to multiply by fractions. You're going to cancel anything that on both sides and then add the energy changes together. And if it asks you for molar enthalpy, you're going to have to divide by the number of moles in your chemical reaction. So if you had 2 moles of, in that last one, if we created 2 moles of carbon dioxide, I would have had to divide it by 2. I think I'd be able to get this thing around my ear enough time. I've done it this week. Okay, everybody got that down? So, determine the molar enthalpy of formation of butane from what we have given you here. What's butane up there? Okay, probably, maybe not. We're looking for the formation of this. So step 1, Crap. Step one, write down formation of butane. I need carbon. I need hydrogen. Okay, so it's a formation reaction. So my elements, carbon plus hydrogen to give you butane. Now, if you don't know a chemical name, quite often they're in your heat of formation page on, I think it's page 4 of here. You have all of these guys. So that's one place to find them. Now we know it's in there, so we could find it. But now, step 2, we are given 3 reactions. I look at reaction 1, and I've got butane on the reactant side, but I want butane on the product side. So I'm going to take reaction 1, and I'm going to flip it. Oop, what did I forget to do? Balance it. Balances nicely, 4, 5. So, take step 1, we're going to basically 4 CO2 plus, where was I? 5 water. It is gas. Now I forgot to put the energy in here. I'll just put it underneath for now. Because I flipped the entire reaction, I need my energy on this side. The next thing that I look at, I need 4 carbons. So that's reaction 2, which is for me the second reaction. I usually number them. I need 4 of those carbons. So I'm going to have to multiply reaction 2 by 4. $1,400 to 16, almost 1,600. So make sure that you're multiplying by the energy by that amount. And I also need 5 hydrogens. What do I have to multiply 2 by to get to 5? Use a decimal if it's really important to you. I use 5 halves. So I'm going to take reaction 3, multiply by 2.5. That gives me 5H2 gas plus 5 over 2 O2, 5 water, and okay. Now, you can take that energy off to the side. That's not a problem. I'm just going to leave it in, but let's look what we have. I've got 4 CO2s on as a reactant, 4 CO2 as a product. They didn't change. I'm not going to bother writing it down. I've got 5 H2O as a product, and I've got as a reactant, and 5 H2O as a product. I'm not going to bother writing it down. I have 6.5 oxygen combined between these two. Over here, this is 6.5. So again, those guys don't need to be written down. Twenty-seven 83.0 kilojoules. Now, again, I would probably not write down this. I have energy on both sides. Well, the difference between those two numbers is 125. I have more energy over here. Okay, so I have my products, C4H10 plus 125.6 kilojoules, and I'll just copy down what I have over here. So, the flippy part, that's the part that gets us, because again, it's an art. You don't really, there's no one way to do it. You have to do it. Okay, what do I do first? What can I do first? I may do it slightly differently than you guys do. Maybe you guys started with the carbon. What I would suggest is start with the compounds first. Then, if you have to, do the elements. Leave hydrogen and oxygen till the end. There are so many different things where they need to be placed at the end. Now, here the question asks for molar enthalpy. We have 125 kilojoules to create 1 mole of butane. So and I'm going to make a mistake. I just did. What haven't I communicated to you? By writing down the 125? Aurora? Okay, I'll do that in a second. But what didn't I communicate by just writing down a positive 125? Yes? It is a negative sign. I need a negative sign there to indicate that this is an exothermic reaction. Okay? This tells me it's an exothermic here. Now I need to tell you that it's an exothermic there. So negative 125.6 kilojoules per mole, if assuming you can read my writing. Okay. So communication is a very important part to this too. I think I'm just going to leave it here. Now, again, I'm asking you for a formation of dinitrogen pentaoxide. Slightly different way of putting the energies, but it's all fine. Dinitrogen pentaoxide. Well, that means I have 2 of those, 5 of those. I need, because it's formation, I'm going to need nitrogen plus oxygen. This is one of the few times I'm going to worry about balancing my oxygen first. I'm going to put a 2 here to give me 10 oxygens. I'm going to put a 5 there to give me 10 oxygens. And then I'm going to put a 2 here to give me my required number of nitrogens. So we're trying to create this. I believe there's a page on the other side, is there not? Yes, good. Okay. So, which one do you want to start with? Well, again, the one that jumps out to me right away, I need to start with this one. I need two of them, and I need them on the product side. Sean, which equation do I have to manipulate to get that? Number 2. It's the only one that contains it, right? So I'm going to take number 2. I'm going to double it, and I'm going to flip it. I do this to keep track of what I'm doing, because it reminds me to do that to the energy too. So now I've got 4 HNO3, and that will give me 2 of my dinitrogen pentaoxide and 2 water. My delta RH is going to be positive 154 kilojoules. As I flipped it, hence the positive, negative becoming a positive and doubling it. Now, as I said, leave the oxygen till the end. We need 4 nitrogens. Okay, well, let's just take equation number 3, multiply it by 4. Nope. And that is wrong. Okay, no, maybe not. And that gives me 4 HNO3s. Now notice again, I had 4 nitric acid over there. I have 4 nitric acid here. That's going to allow me to cross that off. Now, my delta RH is going to be positive 696 kilojoules. So I have my nitrogen. I have this in my proper spot. Oh. I have too much oxygen. I only need 5 of them. Now, this is where I get into this idea of canceling. I'm not going to worry about oxygen. I also have this 2H2O over here that I want to get rid of because I don't have H2O in this reaction. So I'm going to take reaction number 1 and I'm going to flip it. This is that art part of it. I have too many oxygens. I have too many water. I have too many hydrogens. I put gas there, I guess, liquid, so. And did somebody catch my mistake? Right here. I didn't flip this one. This should be a negative. Okay. So here I had to look at, okay, how do I cancel? And I might want to put the 2 that I had there. So my 2 waters go away. They don't need to be written down. My 4 nitric acids don't need to be written down. My 2 hydrogens don't need to be written down. And this 1 oxygen will turn that into 5 oxygens on that side. So we have our 2 nitrogen gas plus our 5 oxygen yields our 2 N2O5 gas. So our reaction is what we wanted. Now we just have to add these guys together. And I just made another stupid mistake on my calculator. Get a positive 30 kilojoules. Just going to go back up here. And because it says molar enthalpy, and the way I have my reaction balanced, I have 2 moles of my dinitrogen tetraoxide. So the molar enthalpy is positive 30 kilojoules divided by my 2 moles, positive 15 kilojoules per mole. Oops, might want to put the mole down. Okay. So, and that's the process. As I said, going through this is a lot of an art, and you have to get used to that. So the only way that you can really practice or get this is to practice on it. So where did my homework go? There it is. So in your textbook, 1 to 4 on page 504, lab exercise 11B. So what you're going to have with 11B is you're going to do a prediction using Hess's law, flip, etc. And you're going to do a calorimetry part to actually determine the experimental. Okay. Please ask me questions as you need to. Why did this stop?